Section 15.4, Applications of Double Integrals. In Section 8.3, we found the total mass of a lamina with constant density rho, but now that we have double integrals, we can find the total mass of a lamina with variable density. So the density of the lamina is given by some function of x and y rho. So suppose a lamina occupies a region D of the xy plane, and its density is given by this rho of xy, where rho is a continuous function on D, and the total mass of the lamina is given as the limit of the double Riemann sum of rho at certain sample points, xij star, yij star, delta A, and that's just the double integral of rho. Similarly, if an electric charge is distributed over a region D and the charge density in units of charge per unit area is given by sigma of xy, then total charge is given by the double integral of sigma. So we just use sigma instead of rho for charge. So as an example, how about we look at when charge is distributed over the triangular region in our figure over here, so that the charge density sigma of xy is measured in coulombs per square meter, and it's equal to xy in this case. How about we find the total charge? So our total charge Q is equal to our double integral over D of sigma of xy dA, and we're told that it's over this triangular region. So it looks like if we look at y, we can make this a type 1 region. We integrate from bottom to top, so we integrate from 2y equals functions of x, so we'll integrate from y minus x to 1 for y, and then from 0 to 1 for x. So put x on the outside, we'll put y on the inside, and our function for sigma is xy, so we'll plug that in, and then we first do y and then do x. So during our double integral, we get that it's the integral from 0 to 1 of x times y squared over 2, because first we hold x constant, and we evaluate from y equals 1 minus x to y equals 1. And then we plug in, and we get the integral of x over 2 times 1 squared minus 1 minus x squared dx, which is just half times the integral from 0 to 1 of 2x squared minus x cubed. And that just becomes half of 2x cubed over 3 minus x to the 4th over 4, evaluated from 0 to 1. We do our antiderivative, and we get 5 over 24 coulombs. Next, suppose a lamina occupies a region D and has density function rho, and the moment of the lamina about the x-axis is defined similarly to the way we did in section 8.3 in single variable calculus, where we take the distance from the x-axis. Remember, if we're drawing some x and y axis, then here's y and here's x, and we want the distance from the x-axis for a point, so that's some y value. So we multiply our density function by y. Similarly, if we want the moment about the y-axis, then we need the distance from the y-axis, which is some x value. So we multiply by x, and then when we take the double Riemann sum, all of our sample points just kind of disappear and become x and y values. The coordinates x bar, y bar of the center of mass of a lamina occupying region D and having density function rho are also defined pretty much the same way as we did before. We take the moment about the y-axis and divide by m, because that's the distance, that's the x distance, so that's our x bar, and so that's just 1 over m times the integral with an x thrown in, and then similarly for y. So remember, the mass is the double integral over rho as we saw before. The cool thing about the center of mass is that the lamina will balance horizontally when supported at its center of mass. So in this case, it's not right in the middle, because remember, we have some density function rho that's variable in this lamina. So this part, I guess, must be a little bit more dense than this part in order to compensate for it and have this thing balance. Find the mass and center of mass of a triangular lamina with vertices 0, 0, 1, 0, and 0, 2 if the density function is rho equals to 1 plus 3x plus y. So how about we draw our triangular lamina? Let's see. So something like this, where we connect from 0, 2 to 1, 0. So this is 1, 0, and this is 0, 2, and then here's my origin, and this is my region D. So it looks like I need to figure out what this boundary line over here is, but that's easy enough because it's just the equation of a line. If you notice, the y-intercept is 2, so you could say it's y equal to 2, and then the slope goes down 2 over 1, so minus 2x. And we want the mass and center of mass. So how about we first find the mass, because we have to do 1 over the mass times our other integrals. So mass is the double integral over d of our density function rho. And in this case, it looks like we can describe d as a type 1 region again. We can integrate from bottom to top. So it looks like our bottom function is 0 and our top is some function of x, y equals 2 minus 2x. So that's where y goes from. And the outside of x goes from 0 to 1. So we'll go from 0 to 1 on the outside. And then from 0 to 2 minus 2x. And we integrate 1 plus 3x plus y. First with respect to y and then with respect to x. So that becomes the integral from 0 to 1 of y plus 3xy plus y squared over 2, which we evaluate from y equals 0 to y equals 2 minus 2x. And then we take the 4 out. We get the integral from 0 to 1 of 1 minus x squared, which is 4 times x minus x cubed over 3 from 0 to 1. And that's just 8/3. Okay, so now let's find x bar, the x coordinate for our center of mass. So that's 1 over the total mass times the double integral over d of x times rho, and rho is a function of x and y. So this is just going to be 3/8 times the iterated integral from 0 to 1, and then from 0 to 2 minus 2x of x plus 3x squared plus xy dy dx. And that's 3/8 times the integral from 0 to 1 of xy plus 3x squared y plus x times y squared over 2 from y equals 0 to y equals 2 minus 2x. And that becomes 3 over 2 times the integral from 0 to 1 of x minus x cubed, which is just 3 over 2 times x cubed over x squared over 2 minus x to the 4th over 4 from 0 to 1, which is 3/8. So that's interesting. We had 8/3 the total mass and 3/8 for the x bar. Let's find the y bar now. So for y bar, we have 1 over m times the double integral over d of y times rho of xy dA, and that's 3/8 times the integral from 0 to 1 of the integral from 0 to 2 minus 2x y plus 3xy plus y squared dy dx, and that's 3/8 times the integral from 0 to 1 of y squared over 2 plus 3x times y squared over 2 plus y cubed over 3 from y equals 0 to y equals 2 minus 2x, which is 1/4 times the integral from 0 to 1 of 7 minus 9x minus 3x squared plus 5x cubed dx. And taking our antiderivative, we get 1/4 7x minus 9 times x squared over 2 minus x cubed plus 5 times x to the 4th over 4 from 0 to 1, which is 11/16. So our center of mass, x bar, y bar, is equal to 3/8 11/16. And that means that if we're going to put this in our triangular region, it's somewhere over here. So that's where 3/8 11/16 is. The density at any point on a semicircular lamina is proportional to the distance from the center of the circle. Let's find the center of mass of the lamina. So first, how about we draw it? So we have some semicircle, and they didn't tell us what the radius of this thing is, so how about we just say it's A. So we'll put minus A over here, and I'll draw the lamina like that. So this is also A, and we can say that this is our region D, which has the equation of a circle x squared plus y squared equals a squared, but it's just the top half of that circle. So we need a density function also. They didn't give us that either. So we said rho of xy is proportional to the distance from the center of the circle. So that means it's some constant times the distance from the center. So I'm going to make the constant k. The distance from the center is just the distance formula, so that's the square root of x minus 0 squared plus y minus 0 squared, so that's just the square root of x squared plus y squared. And this means that we can describe our region D now. Well, this figure means not the density function, obviously, but as some polar region, because notice it's nice and circular, or it should be if you have more steady hands. So it's probably more convenient to do our integral in polar coordinates. So we'll say it's all of the r thetas such that it looks like the radius goes from 0 to a. So we could say r goes from 0 to a, and it looks like theta just goes halfway around, so up to 180, so that's up to pi. So theta is between 0 and pi. And this means that our total mass is the double integral over d of rho of xy dA. So that's equal to the double integral over d of our constant k times the square root of x squared plus y squared for rho dA. And that's equal to the polar integral, where outside we have theta from 0 to pi, and inside we have r from 0 to a of k times, well, now we have to convert this, but notice x squared plus y squared is equal to r squared in polar coordinates. So the square root of x squared plus y squared is just equal to r. Next, remember dA is equal to r dr d theta. So evaluating this integral, we can pull out the constant k. Notice that we have functions of r separate from functions of theta. We just have r squared for the function of r. We have just d theta. So we can separate our integral into the integral from 0 to pi of d theta times the integral from 0 to a of r squared dr. So that's just k times pi for the d theta, and then r cubed over 3 from 0 to a, which is just k times pi over, k pi times a cubed over 3. So that's our total mass. Now we want the center of mass. So notice that the x-coordinate is kind of easy. This thing is perfectly symmetrical, and the density function is also symmetrical. So there's the same amount of density on the left and right. So that means that our x bar must be equal to 0, must be in the center somewhere by symmetry. So that's cool. When your density function and your lamina both have symmetry about an axis, that basically gives you one of the coordinates of your center of mass for free. Now let's get y bar. So unfortunately there's no symmetry on top and bottom over here, so we have to compute that. So that'll be 1 over the total mass times the double integral of rho of xy dA. Oh, I forgot my y. That's the whole distinguishing point, is that we throw a y in here. Okay, so throwing our y in there, we get 3 over k times pi a cubed, because we take 1 over m, and then we have 0 to pi for our first integral, and then 0 to a for our inner one of r sine theta times kr r dr d theta, because y is just r sine theta. Okay, let's keep going. So this becomes 3 over pi a cubed times the integral from 0 to pi of sine of theta d theta times the integral from 0 to a of r cubed dr. Because again, we have separate functions of r and theta, so we can split the r integral. So now we have 3 over pi a cubed times minus cosine theta from 0 to pi times r to the 4th over 4 from 0 to a. So that's just 3 over pi a cubed times 2a to the 4th over 4, which is 3a over 2 pi. Cool, so that means our center of mass x bar, y bar is equal to 0, 3a over 2 pi. So that means it's like, I don't know, somewhere over here, where this is the point 0, 3a over 2 pi. So not quite halfway on the y-axis. The moment of inertia, also called the second moment of a particle of mass m about an axis, is defined to be m times r squared, where r is the distance from the particle to the axis. The moment of inertia of the lamina about the x-axis is defined to be ix, which is the limit of the double sum of yi squared rho delta a. Since we need the distance from the x-axis, we need to throw an extra y in there. And then similarly, the moment of inertia about the y-axis is defined to be iy, where we throw an extra x in there. So we have x squared rho when we integrate. And the moment of inertia about the origin, also called the polar moment of inertia, is defined to be the sum of these two guys. We take the xij star squared plus yij star squared, so we basically just take this plus this. That's pretty much what it ends up becoming. So let's do an example and find the moments of inertia ix, iy, and I0 of a homogeneous disk D with density rho of xy equals rho. So that means that we're looking at something with a constant density this time, so it should be pretty easy to integrate. And the radius is a. Okay, so the radius is a, it's a disk, so that means the boundary of the disk is x squared plus y squared equals a squared. So that means we're looking for everything inside of x squared plus y squared equals a squared. So that means we can write our region D again in polar coordinates. So we can write it as the set of points are theta, such that this time theta goes all the way to 2 pi because it's not semicircular, it's just a complete circle. And r goes between 0 and a. So now we should probably get our moments of inertia, but using the fact that ix plus iy is I0, and we have symmetry about our lamina and our density function's constant, we should probably find I0 first and then use that, take advantage of it to get the other ones. So we calculate I0 as the double integral over d of x squared plus y squared times our function rho, which in this case is just a constant, so I'll just call it constant rho. And since rho is constant, I can pull it out and just get the integral from 0 to 2 pi for theta, and then 0 to a for r of r squared for x squared plus y squared, and then dA is r dr d theta. So rho is still out. I can split my integral into the integral from 0 to 2 pi of d theta times the integral from 0 to a of r cubed dr, which is 2 pi times rho times r to the 4th over 4 from 0 to a, which is pi times rho a to the 4th over 2. And then, like I said, by definition, we have ix plus iy equal to I0, but we also have that ix is equal to iy because we have a symmetrical lamina and our density function is just constant. So ix equals iy by symmetry, and that means that we have ix equal to iy, so that's just going to be I0 divided by 2. We just replace one of these guys with the other one. So I just have to take rho pi, I just said pi rho, I reversed it, but it's pi rho a to the 4th, and then instead of over 2, it's over 4 because I just divided by another 2. The radius of gyration of a lamina about an axis is the number r such that m times capital R squared equals I, where m is the mass of the lamina and I is the moment of inertia about the given axis. In particular, the radius of gyration y double bar with respect to the x-axis and radius of gyration x double bar with respect to the y-axis are given by the equations m double bar y squared equals ix, m times x double bar squared equals iy. So how about we find the radius of gyration about the x-axis of the disk that we just looked at in the previous example. So we need the total mass m so that we can take ix and divide by that to get y double bar squared. So remember that mass is density times area. So our density is rho, and the area of the disk is pi r squared, but r was a, so that's just pi a squared. Okay, so now we can get y double bar. So y double bar squared is ix divided by m. So ix divided by And that's just going to be 1/4 pi rho a to the 4th divided by rho pi a squared, which is a squared over 4, with everything cancels. So we can take square roots and we get that y double bar is equal to half a, or a over 2. Next up, let's do a little probability. So like we did in section 8.5, we can get probability by integrating a density function. So in this case, we have to define a joint density function because we have two continuous random variables, so we get a multivariate function. So it becomes a double integral. So the probability that xy is in some region D is just a double integral over D. In particular, if the region is a rectangle, then the probability that x lies between a and b and y lies between c and d is just an iterated integral. Now, because probabilities aren't negative and are measured on a scale from 0 to 1, our joint density function must be greater than or equal to 0, and its integral, or double integral, over the entire plane, R2, must be equal to 1. So this means that if we're looking at the double integral over the entire plane, then we split that into the iterated integral from minus infinity to infinity, minus infinity to infinity, and we say that that's just the limit of the double integral over a disk as the disk keeps getting bigger and bigger and bigger. Limit of a to infinity where it's disk of radius a. So that's what we mean when we say we integrate over the entire plane. As an example, let's try to find c for this joint density function for x and y, and then try to find the probability. So in order to find the constant c, let's take advantage of the fact that the double integral of this thing has to be 1 if you integrate everywhere. So I could set 1 equal to the iterated integral from minus infinity to infinity, minus infinity to infinity of f of xy dy dx, and notice that it's 0 if you go outside of 0 to 10, 0 to 10. So that means that my integral would be 0 outside of that area, so I can just consider the integral from 0 to 10 and 0 to 10, because everywhere else it's going to be inconsequential. And then f of xy from 0 to 10, 0 to 10 is this function over here, so I'll just put that in there. So that's kind of nice, I don't have to worry about taking limits or anything else. So then we pull out our constant c, and we get the integral from 0 to 10 of xy plus y squared from y equals 0 to y equals 10. And that just becomes our constant c times the integral from 0 to 10 of 10x plus 100. So integrating that, we just get 1500. So it's 1500c. So that means that 1 must equal 1500c. So I can divide by 1500 to get c. So that means that c must be 1 over 1500. So now let's get the probability that x is less than or equal to 7 and y is greater than or equal to 2. So that's just equal to the integral from minus infinity to 7 for x, and then 2 to infinity for y of f of xy dy dx. So remember, there's no contribution beyond 0 for either x or y, so that means that we can integrate from 0 to 7 and then from 2 to 10, because beyond 10, below 0, it's just 0 anyway. And then f of xy is c times x plus 2y, but we calculated c was 1 over 1500, so I'll plug that in now. and x plus 2y dy dx. So that's equal to 1 over 1500 times the integral from 0 to 7 of xy plus y squared from y equals 2 to y equals 10, which is just 1 over 1500 times the integral from 0 to 7 of 8x plus 96 dx. And evaluating that, we get 868 over 1500, which is roughly 0.5787. Next, suppose x is a random variable with probability density function f1 of x. Y is a random variable with density function f2 of y. Then x and y are called independent random variables if their joint density function is the product of their individual density functions. So that means we can split our multivariable function into some function of x times some function of y. So we'll use this pretty often to find joint density functions using our probability density functions that we already found in single variable calculus in section 8.5. So say the manager of a movie theater determines that the average time moviegoers wait in line to buy a ticket for this week's film is 10 minutes and the average time they wait to buy popcorn is 5 minutes. Assuming that the waiting times are independent, we'll find the probability that a moviegoer waits a total of less than 20 minutes before taking their seat. So I have f1 of x given by the probability density function. It's piecewise. It's 0 if x is negative and 1 over 10 e to the minus x over 10 if x is positive. And we calculated this in section 8.5. And then we have basically the same thing for y. So for f2 of y, we have it's 0 if x is negative, and then 1 over 5, because it's 5 minutes for popcorn, e to the minus 1 over 5. And that's if y is negative and if y is greater than or equal to 0. And that means that because these guys are independent, our joint density function of two variables will just be what we get when we multiply these two functions. So that's just 1 over 50 e to the minus x over 10 e to the minus y over 5, assuming that x is positive, y is positive, and 0 otherwise. So if x is greater than or equal to 0, y is greater than or equal to 0, and it's 0 everywhere else. Because obviously the probability that they wait any amount of time when we go backwards in time is 0. Okay, so we want now the probability that x plus y is less than 20. So that would be the probability that xy is some region D, where D is bounded by the line x plus y equals 20, and our axes, because we can't have negative times. So how about we draw that? So then the line x plus y equals 20 just has intercepts 20 for x and y. You just plug in 0. So that means it looks like this. So you put 20 over here, 20 over here, and this is our region D, such that this is the probability that xy lies inside D. So by definition, that's just the double integral over D of our joint density function. So looking at our region, it's pretty easy to make it a type 1 region. So we'll just have x go from 0 to 20, and we'll have y go from two functions of x. So it looks at the bottom would be 0, and then it goes to the top of y equals 20 minus x. So we'll go from 0 to 20 minus x for y, and we have 1 over 50 e to the minus x over 10 e to the minus y over 5 dy dx. So that's 1 over 50 times the integral from 0 to 20 of e to the minus x over 10 minus 5 e to the minus y over 5. And we evaluate this from y equals 0 to y equals 20 minus x. So let's keep going. We get 1/10 times our integral from 0 to 20 of e to the minus x over 10 times 1 minus e to the x minus 20 over 5, because we just evaluate and pull out the minus 5. Well, we don't pull out the minus part, we put in the minus part, just switch the order, but we pull out the 5. And we get 1/10 integral from 0 to 20 of e to the minus x over 10 minus e to the minus 4 e to the x over 10 dx, which is 1 plus e to the minus 4 minus 2 e to the minus 2. And using a calculator, it's about 0.7476. So we could say that the amount of moviegoers that wait less than 20 minutes is about 75% of them. If x and y are random variables with joint density function f, we define the x-mean and y-mean, also called the expected values of x and y, to be mu1 and mu2, where we just multiply by x and multiply by y. So let's use that, because in section 8.5 we looked at the normal distribution for density function, so we can apply that to find a joint density function for the normal distribution. A factory produces cylindrically shaped roller bearings that are sold as having a diameter of 4 centimeters and length 6 centimeters. In fact, the diameters x are normally distributed with mean 4 centimeters and standard deviation 0.01 centimeters, while the lengths y are normally distributed with mean 6 centimeters and standard deviation 0.01 centimeters. Assuming that x and y are independent, write the joint density function and graph it. Find the probability that a bearing randomly chosen from the production line has either length or diameter that differs in the mean by more than 0.02 centimeters. So let's look at our x-mean was mu1, and they told us that that was 4 centimeters. Then our y-mean was mu2, which is 6 centimeters. And sigma 1 is equal to sigma 2. They both have the same standard deviation of 0.01. So as we've seen before, the probability density function for standard distribution, or normal distribution, is 1 over 0.01 times square root of 2 pi, because it's sigma times square root of 2 pi times e to the minus x minus mu, in this case mu1, which is 4 squared over 2 times sigma squared, so that's 0.0002. And then f2 of y is pretty similar. It's just 1 over 0.01 square root of 2 pi e to the minus y minus 6 squared over 0.0002. So we get our joint density function, f of xy, by multiplying these because they're independent. So it's f1 of x times f2 of y. So that's 1 over 0.0002 times pi, because 0.01 times 0.01, and then square root of 2 times square root of 2 is 2, and then square root of pi times square root of pi is pi. And then e to the minus x minus 4 squared over 0.0002 times e to the minus y minus 6 squared over 0.0002. And that's just 5,000 over pi times e to the minus 5,000 and times x minus 4 squared plus y minus 6 squared. Just multiplying e, we just add the exponents. Okay, so if we were to graph this thing, it would look very roughly something like this. It's kind of like a 3D version of our joint density function. Not so good at graphing this thing. I don't know, maybe you could imagine it's like sort of like this thimble. You just take our normal distribution, which is just the bell curve, and you make like a 3D version of it. Okay, so the probability that a bearing randomly chosen to the production line has either length or diameter that differs from the mean by more than 0.02 is probably easiest to calculate by finding the probability that it differs by less than 0.02 and then subtracting. So how about we find the probability that x is between 3.98 and 4.02. So that's the probability that x differs by less than 0.02. And for y, it's the probability that our mean is either, or that y differs from the mean by 5.98 and 6.02. Just took the mu1 and mu2 and go up by 0.02 and down by 0.02. So that's our double integral from 3.98 to 4.02 of the integral from 5.98 to 6.02 f of xy dy dx, which is 5,000 over pi times the integral from 3.98 to 4.02, the integral from 5.98 to 6.02, e to the minus 5,000 x minus 4 squared plus y minus 6 squared dy dx. And using a calculator, we get that's about 0.91. So that means that we can now get the probability that x or y differs from its mean by more than 0.02 by subtracting. So we get that that's about 1 minus 0.91, which is 0.09.